Okay, so let's take a look at what's going on here. So in A, we have difference of perfect squares. We have a squared minus b squared. So we're going to use our factorization of a's difference of perfect squares, which is a minus b times a plus b, to get 5x minus 2 minus 4x minus 2 multiplied by 5x minus 2 plus 4x plus 2. Okay, notice in this first one here, when I subtracted the 4x plus 2, really I have to distribute the negative to the 4x, which gives me a negative 4x here. And I also have to distribute the negative to the positive 2, which gives me a negative 2. So we need to be careful about that. Easy place to make a mistake. Okay, so let's collect terms and see what we have here. So in the first factor, we're going to end up with a 5x minus 4x, or just x. Minus 2 gives us minus 4. On the second factor, we're going to get 5x plus 4x, or 9x. And minus 2 plus 2, so we just have 9x. Our denominator is 3x times x minus 4. So I'm not expanding because I want to see whether there's any simplification I can do while they're in their factored form. And there is, in fact, because the x minus 4's cancel out, the x's cancel out. 9 divided by 3 gives us just 3. So what that means is no matter what value we plug in for x, that thing is just going to be equal to 3. Okay, let's take a look at this next one here. All right, so this is like the problem we had the other day. We have a number of things we need to simplify first. So let's start with the top. We have a fraction or two fractions with different denominators. And so we're going to make each of them have the same denominator by multiplying the second fraction by x over x, the first by y over y. The reason we're doing that is because this will give us both fractions having the same denominator of x times y. So we're going to end up with 6y, 6 times y here, and 3x plus 3x over xy. Okay, that's going to be our numerator. Here on the denominator, we want to say, all right, we have this negative 1 exponent, so we're going to replace that with 1 over xy. So what the denominator is going to end up being is 2y plus x over xy. Okay, so you can see some real potential for simplification here. So one way to think of this is we are taking this top fraction here and we're multiplying it by this bottom fraction, which means we're doing the equivalent of multiplying by the reciprocal of the bottom fraction. So we end up with 2y plus x as our denominator here. All right, when we look at this now, we can see that we can cancel out the xy's, and we end up with just 6y plus 3x over 2y plus x. And guess what? 3 times 2y plus 3x over 2y plus, over, this should be a, let me erase this here. This should be just an x, so we end up with 2y plus x canceling out, and again, we end up with just 3. So no matter what values of x you plug in, you're just going to get 3. Okay, now let's look at this simplification here. So we have a fourth root. So what we're looking to do is pull out any perfect fourth powers. So for example, 2 to the fourth is equal to 16. So what we're going to do is we're going to break this into two radicals, and those will be multiplied together. In the first, we'll have all our perfect fourth powers. So we have 16, which is 2 to the fourth. And when we factor that out of 64, we're left with 4. The largest perfect power of 4 in x to the ninth is x to the eighth, because 8's divisible by 4. That's going to leave us an x here. And we can also factor out a y to the fourth, and that leaves us a y here. So now I want to take the fourth root of everything in here, which is going to give me 2x squared y. And then we still have the radical here. This is multiplication. And so we're talking about the fourth root of 4xy. So this is our simplification. And again, what we did was we looked for any number that is either a variable raised to the fourth power that we could factor out, or a number raised to the fourth power that we could factor out. We put all of those under the first radical, and we put what was left over after we factored into the second radical. And then we took the fourth root of this first radical and we multiply it by the radical which contained the factors that we still had after we factored out the perfect powers of 4. Okay. Next, all right, so now we have this thing again. And what are we going to do? We're going to multiply top and bottom by the conjugate, root 15 plus root 3. And again, the reason that we do that, as we've said many times, is we want to get that factorization pattern of a minus b times a plus b, which means that we're going to end up with a denominator of a squared, or 15, minus b squared, minus 3, which means that we're going to have a denominator of just 12. Our numerator here, okay, we're going to do root 15 times root 15, which gives us 15. We're going to do root 15 times root 3, which gives us root 45. We're going to have negative root 12 times root 15, which is going to give us negative root 180. And we're going to have negative root 12 times root 3, which is going to give us negative root 36. All right. Now we need to see if we can do any simplification of these radicals. All right, so we have our 15. We know that this, I'll come back to that. So root 45 can be factored into root 9 times root 5, which is going to be 3 times root 5. Negative, so 180 can be factored into 36 and 5, which is going to give us 6 root 5. And then root 36 is just going to give us minus 6. So when we collect all these, we end up with 9, 15 minus 6. 3 root 5 minus 6 root 5 is negative 3 root 5, all over 12. And that can be all divided by 3. So we're going to end up with 3 minus root 5 over 4. Okay. So that actually is simpler than our original expression. That's not always going to be the case, but what is going to be the case is that we've removed any radicals from the denominator, and that will make it easier to work with. Okay, so let's continue on to the next page here. Okay, so now we have some solving to do. Okay, so we take a look at A, and we need to find the base that's common to both sides here, and that's going to be a 7. So we end up with 7 squared to the 4x minus 5 is equal to, and this is 7 cubed, to the 2x plus 1. Okay, so now we're going to, because we're taking 7, raising it to the second, and raising it to the 4x minus 5, we're going to get 7 to the 8x minus 5 is equal to 7 to the 6x plus 3. And when the values are the same and the bases are the same, then the exponents have to be the same. So now we have a new equation, which will be a lot easier to work with. 8x minus 5 equals 6x minus 3. And we're going to subtract 6x from both sides to get 2x minus 5 is equal to negative 3. We add 5 to both sides. We get 2x is equal to 2. X then is equal to 1. Okay. All right. For B, we have 1/8 to the x plus 5 and 32 to the x minus 3. All right. We know that the bases here are going to be 2, and this is to the negative 3. To the x plus 5 equals 2 to the 5th to the x minus 3. Okay, so we're going to multiply and get negative 3x minus 15 is equal to 5x minus 15. And notice here I skipped one step where I didn't write this out as 2 to the negative 3x minus 15 and 2 to the 5x minus 15. I just went right to setting the exponents equal. Okay, so we're going to add 15 to both sides. We get negative 3x is equal to 5x. Okay, what value of x makes that true? Well, let's add 3x to both sides. We get 0 is equal to 8x, so x has to be equal to 0. That's our solution. Okay, time for a little factoring. All right, let's take a look at this first one. The first thing is we always look for common factors, and we can see that actually in each one of these we have an x. So we can factor out x from all of these to get 9x squared minus 24xy plus 16y squared minus 25z z squared. Okay, so we have 4 terms here, which means that either we're going to be factoring by grouping, or we're going to be looking for one of our other factoring patterns. And in fact, we have one here with this 9x squared minus 24xy plus 16y squared is a perfect square trinomial. And I know that because 9x squared is a perfect square with the square root of 3x, so we have 3x squared. We have 4y squared, so the last term is also a perfect square. And the middle term is equal to double the square root of these two terms, or in this case, the negative square root, which is fine. So we have 3x times 4y is 12y, so we have negative 24xy. So then what we can say in the end is that this whole thing as a perfect square trinomial is equal to 3x, and in this case it's going to be minus 4y squared. We still have our minus 25z squared, and we still have our x. Okay, so this is what we have now. Okay, so now we have a difference of perfect squares where we have a squared, 3x minus 4y squared minus b squared, where b is actually going to be the square root of 25z squared, or 5z. And again, all still multiplied by x. So we're going to have x times 3x minus 4y plus 5z times 3x minus 4y minus 5z. Okay. All right, let's look at this next one. 2ac minus b cubed plus 2ab squared minus bc. All right. Well, this looks like it's going to be with the 4 terms and the 3 different variables and none of our recognizable factoring patterns. We're going to be factoring by grouping here. All right, so ac and b cubed have nothing common, so I'm going to rearrange here to get 2ac plus 2ab squared minus b cubed minus bc. All right, so let's pull out the common factors of the first two, which is going to be 2a, leaving us with c plus b squared, minus b is our largest common factor, and here we're going to have again b squared plus c, which is really just the same as c plus b squared. So we end up with 2a minus b times b squared plus c. Okay, let's solve this by completing the square. Last problem. We're going to use fractions. All right, so first step, we have an equation, so we can divide everything through by 3 to get that first coefficient to be 1. So we're going to end up with x squared minus 3x is equal to 10 over 3. Okay, so to make this left side a perfect square trinomial, we have to take half of the coefficient of the x, which is negative 3, and square it and add it to both sides. So we get x squared minus 3x equals 10 thirds. All right, half of negative 3 is negative 3 halves. Squared is plus 9 fourths. Plus 9 fourths. Well, on the left, this is just going to give us x minus 3 halves squared. And that was the whole goal, to get this into a perfect square trinomial so we could factor it and get x minus, in this case, x minus 3 halves squared. Okay, on the right side, let's combine these fractions. So we're going to multiply 10 thirds, top and bottom, by 4 over 4 to get 40 over 12. And we're going to multiply top and bottom of, we're going to multiply top and bottom of 9 thirds by 3 to get 27 over 12, which is equal to 67 over 12. All right, so what do we end up with? X minus 3 halves squared is equal to 67 over 12. Square root both sides to get x minus 3 halves is equal to plus or minus square root of 67 over 12. And so we're going to get x is equal to 3 halves plus root 67 over 12, and or x is 3 halves minus root 67 over 12. Now I could also keep going by saying that root 67 over 12 is equal to root 1 over 4 times 67 over 3, which would give us the square root of 1/4, which is 1/2, so we'd have 1/2 times the square root of 67 over 3. So we could also write our answers as, this is getting a little messy here, 3 halves plus 1/2 root 67 over 3, or 3 halves minus 1/2 root 67 over 3.